Good afternoon, everyone, and thank you for attending this webinar. I'm sorry I can't be with you. I should tell you that actually how I came to find out about your organization. Last year, about this time, I was on a flight from Tucson, and I sat next to a gentleman, one of your members, Dick Engel, and who's a mechanical engineer, and we got talking about what we do, and he said, oh, this is interesting. You should come and talk to our group in Indiana. So we managed to have again, it was a webinar, but in October, I gave a 1.5-hour presentation, a much longer version of today's presentation to the Central Chapter. So with the help of the chapter president, Sanders Hillis. So I appreciate the help of all of your members. And today I'll be talking about, similar topic about how to save the decaying infrastructure using composite materials. But because of the time limitation, this will be a shorter presentation, of course. So I won't get into any formulas, but it just give you the overall idea of how these products work. Very briefly, I went to University of Michigan for 10 years. Then I taught at University of Arizona for 28 years. And it was during this time that I started developing these products. And since 1994, I have formed and run this company, QuakeWrap. And just one thing for you to keep in mind, that we have a YouTube channel that has a lot of, if you're interested in these types of projects, we have over 130 of these projects listed, and you can watch those. You can go to any of our websites also if you have a specific question, either about the presentation or about an upcoming project. All of our websites allow you to sign up for a free consultation that you can do on that. So with that, let's just get, I'll be talking today, this is the outline of the presentation. I'll give you a brief introduction to FRP. We start by looking at the wet layup, which was the original idea that we started in the 80s. And that's application to beams, columns, walls, pipes, tanks and chimneys. I just mentioned a couple of those today. And then the bulk of the presentation will be on some of the new products that we have developed, such as this super laminate that has applications in repair of gas pipes, our PileMedic, which we repair for submerged piles and columns, and then the type of Sanebeach construction that we use. And as we go through these things, you'll see, you learn more about how these products are applied. So with that, let me move to the next application of these, which is looking at the materials themselves. These are the most basic types of materials that we started working with in the late 80s. At the time, we were looking at ways or materials that could be used to repair structures, but they wouldn't corrode, unlike steel or concrete, which were the cause of most of the decaying infrastructure. And of course, we wanted something to have high tensile strength. So we started looking at these composite materials. Up until that time, the bulk of use of these materials was in the defense industry. And so they were really not much being used in construction. But here, what you see on the right side, there is a glass fabric that is white colored. The black one is a carbon fabric. And then we have epoxies that are used in the field to apply these. So the basic concept of this can be shown in this video. Let's say here we have several bricks that are not, there's no mortar between them, and we try to make a beam out of them. So we mix this particular epoxy, and which is like a tack coat paste material. We put it on the back of the bricks to make it smooth and get rid of any of the sharp edges. Then the fabric, carbon fabric, is saturated with this other resin, which has a consistency like warm honey. We roll that into the fabric, and then the fabric, once it's saturated, you pick it up, put it on the back of that brick beam, and work it out with your hands to get rid of any of the air bubbles. And this takes maybe about half hour or so to make. The next day, you let it cure in ambient temperature. The next day, in this direction, it doesn't have any strength, but when you put the fabric in tension, it can support the weight of those 4 guys standing on it. Or not only that, you can also drive a truck on it, and you notice that when it fails, it's ultimately the brick that crushes and not the fabric that fails. By the way, on many of these slides, you notice that we have a link to the video on the top. So this one also, if you'd like to watch these videos again, you can refer to those links. FRP products are best for as a tension reinforcement for structures. And remember that we also, in concrete structures, we design as a tension element to take the shear also. They are also ideal for confinement, like wrapping them around a column or a wall. And they have excellent, water and chemical resistance. And remember that for corrosion protection, they create an impervious layer around the structure. And that way, by preventing oxygen to penetrate through that barrier, then we extend the life of the structure significantly. And this is one of the features of these products that we use a lot for our repairs, as you'll see, for corrosion protection. But they're not quite as efficient as they are in tension for compression. So we usually conservatively ignore their contribution in compression. Advantages of these materials: in tension, they're about 3 to 5 times stronger than steel. They're very lightweight. They don't add weight to the structure if you're strengthening the structure. As I said before, corrosion resistance and chemical protection they're great for that. Of course, they're waterproof. Because of these, construction goes really fast because you don't, everything is made and cut to the size that you need in the field. And as a result, they can conform to any shape, so they're versatile. And these few features of our products, for example, our epoxies are 100% solid and non-toxic, and we even have approvals for potable water pipes and tanks, which is one of the things we repair a lot. So in general, when you look at these with relatively a small investment, you can fix your infrastructure and give it a lot of life. And as you see in some of these examples that I'll be showing you now, we look at some like beams and columns, so you get a flavor for what kind of repairs can be done with these products. This is a case about 15, 20 years ago, just a sample project. It's a hospital that they wanted to put a 5-ton equipment on the 2nd floor. And obviously the floor was not designed to take that additional load. So we put these carbon strips, embed them in the concrete slab at the right locations where the stresses are maximum. And then, the floor can be strengthened in a few hours, and you can put the heavy equipment. This is another recently completed project that we did, a culvert under Interstate 10 in Phoenix. And this road portion that you see circled is being expanded. So they wanted to extend the culverts at the same time when they were looking inside of the culvert that is carrying a part of the Arizona, Central Arizona project water. It's called the Western Canal. So the culverts, 2 box culverts, they were corroded at the top. And here, as you can see, the cross section of the box culverts, they're about 14 feet wide. And there was some corrosion at the top that they wanted to repair and strengthen. So the repair included, in this case, we embedded some cathodic protection system also for some of the corroded rebar. And then those were patched up. And then on top of that, the fabric was installed. We would divert the water from one of the box culverts to the other. Once this one box culvert was fixed, then we would divert the water to this one and do the other one. So this is the finished project after the entire ceiling has been strengthened with a layer of carbon fiber. In this particular project, for example, these repairs took only 2.5 months, and it cost about $1.3 million to do 380 feet of these box culverts. And that was compared to an estimated $25 million to rebuild these. So you can see that the cost savings and virtually no loss of or no traffic control. In this case, nobody knew that the work was being performed. Another application here is for construction errors. in this case, this was a brand new bridge that was built on, again, on Interstate 10 in outside of Lordsburg, New Mexico, about 12, 15 years ago. It's a 9-span bridge. The slab is about 12.5-inch thick. And by mistake, the contractor left half of the steel out of one of the bridges. On the other one, they caught the mistake and they fixed it. But this one, which was the westbound bridge, didn't have half of the steel. And then as we were looking at it, you could see the cracks at the mid-span. And as these trucks were going over it, it would bounce heavily and very severely shaking. So instead of tearing the bridge down, this brand new bridge, we just like that brick beam, we applied these strips of carbon under it. And for now, it's been in service, as I said, for some 15 years, and you couldn't tell that there is anything has been done to this bridge. Application of these products in columns, it basically started with some of the seismic work that, after the collapse of some of these bridges. In the older ACI code, for example, the columns, regardless of the size, they require to put a tie every 12-inch along the height of the column. And also usually the ties had a detail where you would just no 135-degree hooks like we require today. So this poor detail resulted that as you load the column would these bars would open up the ties, and then the longitudinal bars would buckle. So as you see, some of the older columns, if they are spiral, they perform well, but the tied ones, as you see here, these do not hold so well, and they crumble and crush quickly. So the solution to this, of course, if you confine this with wrapping them, whether it is with steel or with FRP material, if you wrap them, you not only increase the strength of the column, as I'm showing here, it's a concrete cylinder, but the same idea for whether it is a cylinder or a column, that the unconfined one has, performs like this, but when you confine it, not only you increase the strength, but you also increase the ductility or the strain at failure, which is a major benefit for seismic applications. So we had a grant back in the 90s, almost like 30 years ago now, from National Science Foundation, the first grant that NSF gave to any group to do this. So at that time, we were testing multiple samples of bridge columns. And so here's, for example, a column that we were testing, a model of a half-scale model of a bridge column. On the column, we applied a load of about 100 kip with these, the two rods that you see go through, and then at the bottom, we have the two jacks. So that vertical load was applied first, and then we took the top of the column and shake it back and forth, and this is the hysteretic behavior of a typical column like that. These were built according, similar to those old details with large spacing between the bars. So or between the ties. So as you would expect, near the end of the test, or shortly into it, actually, you would start damaging the base of this column. And that's where this plastic hinge is being formed and a lot of concrete crushing. And as you can see in the load deflection curve, after a couple of cycles, the more you push this, the column cannot take any more load, and the loads start to drop. So that is not a good behavior. And in fact, as a part of this study, we took the same specimen that you saw before, for example, cleaned up this bottom portion of it, wrapped it with some of that FRP product that I was showing you before. And then once this portion of it, like the bottom couple of feet of it was wrapped, then we injected resin in here to make sure that all the voids and cracks were filled with resin and they became solid. So then we took this same, damaged and now fixed column and subjected it to the same type of loading. And you see that here, in this case, the load keeps on increasing with every cycle. As we push, it keeps on taking more load, and we ultimately had to stop the test because we ran out of the displacement capacity of our equipment. But it really, the column had not failed per se. And in comparison, if I put on top of that, you see that this is the dashed line was the original specimen that you saw on the last slide. So you see the dashed line shows the original one, and then after it was damaged, when we fixed it, we get a significantly improved behavior with this type of repair. And we have done these types of repairs extensively on a lot of bridge columns in seismic areas and non-seismic areas as well. I wanted to include a few of the jobs that we happen to have done in your state, so you can see some of these and the dates on these slides. Like this one goes like 17 or 18, 17 years ago when we were doing this. Was a column in a bridge, and the problem in this case, for example, was mostly for corrosion repair. And what happened was that the pipe, the drain from the deck of the bridge, they didn't have a pipe to bring that drain all the way down to the foundation. So it was just left at the top, and obviously all of that salt spray that we use in winter to keep the roads clean, it was getting on top of the bridge and then coming down the side and damaging the column. So this is, then we would, in that case, we cleaned up these rebars and patched them, and then we wrapped these with fabric, as you can see. This is the finished product. This, by the way, some of the techniques that we have recently developed, and I'll share with you later in the presentation, you see that in those cases now, we can shorten these repairs by eliminating the need for making the surface smooth so that it can be wrapped with a fabric. I'll talk about that when we get to those slides later. These are again some additional projects that were done in Indiana, and here for protection and corrosion repair again. These bands of glass fabric that are about 2 feet or so wide. They're wrapped, around the column as you go up the height. And as you can see, installation of these goes really easily. You only need a very light man lift equipment in the field, and no heavy equipment is needed. This type of repair, by the way, again, keep in mind that when we wrap the column with this FRP, we are creating an impervious layer that will forever keep moisture and oxygen out of these columns. So, and because for corrosion, you need oxygen to be present, by doing this type of repair, then we are going to prolong the service life of the column significantly. And these are some more recent bridges, again, in Indiana, in a couple of the counties. You probably recognize these counties. They're more towards central Indiana, I believe, but there are some of them that are here. They're going over railroad tracks. These are some of these columns that were being repaired, corrosion damage mostly. Of course, in your state, you don't have much concern about seismic applications. So most of the work that we do in the Midwest is primarily for corrosion repair of structures. I'm going to switch to another application, which is for repair of pipes. So these, and here there's a case. Let me just show you some of these slides. This is a project that we frequently do these for either water and sewer companies, or in this case, this is a mining corporation that they had a pipe that was corroded. And so once you see the hole because of the corrosion. So once this is done, by the way, here, one thing to keep in mind is that you have to make sure that the carbon fiber does not come in contact with steel. So because they act as dissimilar metals, and you could have a corrosion process, galvanic corrosion starting if these two come in contact. So when we are repairing a steel pipe, for example, such was the case here, we first wrap a layer of glass fabric around that pipe. That layer serves as a dielectric barrier. And then on top of that, we wrap the layers of carbon based on the strength and pressure requirements. And so in this case, the first layer of glass has been applied, and it looks like it took 2 layers of carbon fabric to achieve the pressure rating that we wanted. These, can be done. We are doing these for water, oil, gas. They can be done, as I mentioned, on inside or outside of the pipe. On the inside of the pipe, for example, we have, this is for a penstock. We have done a number of these penstock repairs worldwide, but these are usually, they're at this time 80, 90 years old. This happens to be a riveted penstock in North Carolina. So a couple of things to point out. By the way, as you notice, because these pipes are so large in diameter, they allow man entry. So our crew would enter into the pipe typically from an existing access hatch or manhole. Once they get inside of the pipe and the pipe is clean, then these layers of carbon and glass fabric are applied to the surface of the pipe. Again, if it is a steel pipe, we begin with the first layer of glass, and then on top of that, we apply the layers of carbon. Another point to note is that if you have a riveted pipe, for example, like this one, we have to feather those protruding rivets so that we smooth those surfaces, and that is done as a first step by putting a mix of epoxy and mixing it with sand. We can then coat over those rivets and cove them to get them nice and smooth, and then the fabric is applied on top of that. And another thing to mention to you here is that when you put a liner like this over a length of these pipes, at the upstream and downstream point of the termination points, we want to make sure that water does not get behind that liner and cause a separation of the whole liner from the pipe. And this can be achieved by using what is in our industry, it's called Weco seal, or it's basically a compression ring that you put on as you see, these workers are installing that here. So you put that over the end of the FRP and then apply tension to it to tighten it against the surface of the pipe. On the lower right figure, you see the finished pipe. And I just wanted to point out that you see, all this complex geometry that in the pipe. This pipe actually happened to be even the diameter of the pipe reduced several times during the length of the pipe. So by looking at, if we are fixing these in the field, this technology allows you to make the size adjustments easily in the field, and that's one of the benefits of this type of repair. Now I want to turn our attention to this. The rest of these are really some new products that I have developed in the last dozen years or so, and we have about 20 patents on these various systems that I'll be showing you next. So one of these is this super laminate, and what this is a method where we can take layers of carbon or glass, in whatever configuration, put them together, apply a resin to them, and heat and press them together to create a laminate that you see I'm holding here. Now the laminate, what is unique about it is that, as you see, it has enough rigidity. So unlike the fabric that is very flexible, these can kind of like stand on their own, as you can see, but still they are very thin, so they can be twisted, as you see in my hand. typically these laminates that we manufacture, the tensile strength is really high. We can make them as much as 155,000 PSI, but very thin, and that's the challenge of making these, is to make them so thin that allows us to, as you see them, to apply them in some of these different applications that you'll see in a minute. So by selecting the fabrics to be either unidirectional, which means having the fibers in one direction, or biaxial, meaning having it in multiple directions. By mixing and matching these fabrics, we can come up with an infinite number of laminates for, depending on what the application calls for. So one type of application of these is for internal repair of pipes. As you see here, when the pipe is small and you cannot, doesn't allow man entry. So in this case, we can take a laminate. We use these packers, which are these balloons that you see here is being inflated. We inflate the balloon and take a laminate and put this epoxy on the back of that laminate, and then wrap that laminate around the packer, hold it together with a couple of strings, and then the assembly is sent into the pipe. And we usually, like with a closed circuit TV, we monitor the location. When it is at that location of repair, we inflate the packer, the laminate sticks to the pipe, and then we deflate the packer and pull it out. And the sleeve is left in place, and it strengthens the pipe that way. We do this for a lot of like oil and gas companies. In fact, we right now have a $1 million grant from US Department of Transportation, where we are developing this technology for spot repair of oil and gas transmission lines. And for those of you who may not know that, about the size of this industry, according to the US DOT PHMSA statistics, there are 319,000 miles of transmission pipes in the country. Almost like, well over 300,000 miles of these. So these types of repairs can be very helpful for those applications. Another application of this system is for repair of piles underwater. We use those laminates that you saw before. So let me show you, this was a job that we did for the very first time some 12, 13 years ago in Florida. And this is a small pipe. So in the field, the contractor can cut a length of that laminate, apply this epoxy that cures underwater, so we don't need any coffer dams. And then we pick up that laminate, pass it to the guys in the water. They wrap it around the column, but at a distance. Notice that we do not bond this to the column yet. It is sitting apart from that. And then the annular space between this jacket and the column or pile is filled with grout or concrete, and that becomes the finished product. So this type of application for repair of submerged piles has a lot of, there's a lot of interest on this type of technique worldwide. And as you can see here, for example, in this, on the slide here, we have these spacers that, these spacers are custom made for the job, and they accommodate a particular size of rebar, and they have basically the thickness of the annular space here. So the way they are applied in the field, we give these, several of these spacers are passed through a zip tie, and they are snapped around the column or pile. The diver would install these. And then these longitudinal bars are snapped in place, and once that is done, then we can wrap the jacket around this and fill the annular space, with concrete. On these slides that you see, we have different spacers for like an H pile, if you want to repair to accommodate the rebar, in the middle portion of it. And they also create or define the edge distance from the jacket, so the jacket doesn't come in contact with the pile, if that's our intention. So a wide range of these spacers we make, and these have been a part of a multi-year development and testing by the US Army Corps of Engineers that ultimately resulted in the military selecting this pile medic as their only system that they use worldwide. So for the military, we make these kits like the one that you see here. And in each kit, there is about 80-foot long roll, which is 4 foot wide by 80 feet long. It is in that kit, plus a lot of those spacers, zip ties, epoxy cartridges, mixing. It's basically like as if you go to an IKEA store and get the kit. It has everything you need. And the US Navy buys these kits and they send them to different locations all over the world. And they, the sailors, they can just open up the kit. Everything is in there to start preparing the pile, regardless of the size or shape of the pile, because as you saw, these laminates can be shaped to, be conformed to any shape. This system, since its inception, it has been tested by also a lot of different agencies. I didn't, we don't have time to go through all of those details of the test results, but you can look at our websites and, see some of these for yourself, or contact me and I'll send you the reports. Texas DOT did a study of steel H piles at the University of Houston. Caltrans did a study of concrete piles that are getting damaged by earthquake for the same thing. Nebraska Department of Roads did a study of timber piles strengthened with pile medic, as well as that major Army Corps of Engineers that I mentioned, and some other utility companies like Tucson Electric Power for utility poles, which is another application of this. This picture just shows one of the bridges that we had done with this product in Indiana. It's kind of near Gary, Indiana, on Kennedy Avenue, up in that area. But here, these piles that are submerged, they are being wrapped with these laminates. In this case, we were creating about a ½ inch or so annular space that was getting filled with an epoxy resin. So that was mostly for protection of the corroded steel. But we do these also for strengthening, and there's something unique about this that I would like to point out to you here. So in this case, for example, these are some steel 24-inch diameter piles for a client in Texas that, as you can see, we apply or provide some longitudinal rebars around there with those spaces, and then wrap the layers of laminate around it, and then the annular space gets filled with concrete or grout. But in strengthening these, there is something to keep in mind, that if we are, so as you realize, we are creating a ring of concrete, reinforced concrete around that pile. So if the original host pile is made out of timber or concrete, there is good bond transfer between this new ring of concrete and the host structure. But if the original structure is steel, you don't get a lot of good bond transfer. And as a result, we have developed this product called shear wrap. You could use, of course, you could drill through these or weld studs, but in many jobs, welding is not allowed, as was the case here. Because of the flammable material on site, there was no hot works allowed on this site. So we developed this product called the shear wrap. And what that shear wrap does is that we basically make this device that goes around the pile, and then it is torqued to a specific torque that we call for. And the loads are shown as you see here. For example, if this is a pile with the corroded region shown here, we put these shear wraps, based on our calculations, 2, 3, or 4 of them above and below the damage zone. And then when we put the jacket around it and fill it with concrete, now as the load is applied, you notice that as the load pass, once you get to that shear wrap, it transfers into the ring of concrete, and then bypasses the damage zone, and then it goes back down into the good portion of the pile below the region where the repair has stopped. So this provides a continuous load path from the ring of concrete and the original steel structure. we have a similar device for this for H piles that we call shear clamp, and that also works equally well. As I said, for concrete columns like this one that you see, we don't need any of those shear wraps or shear clamps. This happens to be a project we did several years ago for the Nigerian Petroleum Corporation. We repaired about 90 or 100 of these piles. They were 40 feet deep. I like to joke that we are the only ones I know who took $1 million from Nigerians to fix this infrastructure project for them. But these materials outside of marine and piles, in bridges and ports and so on, they also have other applications. So for example, here are some corroded columns like this in a mine. You're near Chicago, for example. If you go to the Chicago anytime, next time you look at these elevated tracks that they have, their L system, and the Chicago Transit Authority, that the owner of these facilities, you'll find out a lot of these columns at the base of them are badly corroded and could be fixed with a similar type of solution. So in those jobs in the mines, for example, without taking the structure out of service, we just repair them, as you see, encapsulate them with that pile medic and fill it with concrete, or if needed, we can also drill and dowel some rebar into the foundation before putting the jacket, depending on the application. And these can be done on cell phone towers. We have done about 150 or so cell phone towers nationwide, as well as utility poles, whether it is timber, concrete, or steel. And here are just like, this is a project for a utility pole that I thought, you might be interested. These are, in this particular site, there were 3 of these at different heights and so on. But, I wanted to point out that, as you see on the upper right picture here, when you have 2 of these poles very close to each other, you can run a saw along the connecting point and create a 1/8 or 1/4 inch gap between these 2, and then the jacket can pass through that little opening and create a shell around the deteriorated pole to fix it. So this is another application. Now I want to switch to the last part of the presentation, which is some of the Sanebeach construction. And with this Sanebeach construction, it is really the concept the same as an I-beam that we use in structural members. So if you look at, let's say if this green thing demonstrates 2 pieces of, let's say, carbon fabric that are bonded together. So these carbon fabric, this is the expensive part of the system. So you don't want to keep on adding more and more carbon layers to achieve stiffness for your structure. If you imagine just like an I-beam, if you separate these by something, lower cost that goes in between them, the farther you spread them, the stiffer it gets. So, you can, if you make them 4 times as thick, it would be 37 times as rigid. So we use that concept and there's a particular fabric that we have that it's 2 layers of glass fabric, top and bottom, but they get saturated together. And during the curing process, the top layer rises from the bottom layer, and you create these rigid 2 parallel plates connected with a series of these webs. It's a very interesting product. So that can be used, the rigidity of that system can be used to make some lighter and lower cost structures, as you'd see what we do with it now. One application of this product is to make a pipe that we call stiff pipe. So this is fairly easy to construct. You make a mandrel like you see here. The mandrel has telescopic arms that you can pull in and out to create the diameter that you want. We'll put on the skin of it a sheet metal typically, and then the layers of fabric, and that 3D fabric and so on are wrapped around that mandrel, and they would cure in ambient temperature overnight. So the next day, then you collapse the mandrel and you pull the pipe, the finished pipe out of the mandrel and repeat that process. So for this particular job that I'm showing you, we were repairing 80 feet of culvert in Australia. And so we made 4 pieces of that pipe, 20 feet long each, as you see here. And then they were shipped to the job site. This is the deteriorated culvert. And it was deformed. So we custom make the pipe to fit the lowest diameter at the lowest point of the pipe or the culvert. And then the pieces were put there and they were pushed into the old culvert, and the edges are connected together with that wet layup system in the field. We can apply the fabric because this is large enough for man entry. And so this is kind of getting close to the finished pipe. And but look at how light this pipe is, that these 2 guys are pushing it by hand with no equipment, just sitting on a couple of those casters, they're pushing it into the pipe. So that, the fact that this is such a light pipe, it makes a big difference for many of these projects. We are now doing a major project in Detroit right now, that this is, as far as we know, it's the largest such pipe made, in the US today. And this tunnel is 17.5-foot diameter. It's a sewer interceptor that is deteriorated. And we are making these 16-foot diameter pipes and slip lining them into the 17.5-foot diameter tunnel and then grout around the annular space. The unique thing that you see, a couple of things to point out, is that this pipe it weighs only 450 pounds per foot, even with this huge diameter. So the entire piece that you see here, about 14 feet long, it's only about roughly 550, 200 pounds in weight. So it's very lightweight. And the other thing is that this technology allows us to make this pipe about an hour away from the project site. If there was right now, the fiberglass pipe manufacturers in US, the biggest pipe they can make is about 10 or 10.5 foot in diameter. So notwithstanding the fact that they can't make a pipe this big, even if they could make it, let's say if the pipe was being made in Texas and this job is in Detroit, you couldn't transport it and be economical for those long distances. We are in fact making these pipes in 14-foot long segments, because two segments of a pipe can be put on a lowboy truck, and then that can go under the overpass bridges and be driven and delivered to the job site. That same technology that we saw to make a pipe, independent pipe, we could use the same one to build a pipe inside of an existing deteriorated pipe, as is the case here we were doing for this tunnel in Minneapolis. So here, this was I think it was a 12-foot diameter tunnel, but a portion of the tunnel was severely damaged and needed repair. And the challenging part to this was that there was a shaft that you would go down, that shaft about 4 foot in diameter, you would go down, but then you had to travel about 3,000 feet to get to this point of repair. So you could not build a pipe and take it into this. So the guys, our crew would go in there once the leakage of the pipe was stopped, and then they would apply these layers similar to the way that we made that pipe, but now we would use the host pipe as our mold or mandrel, and apply the layers to the inside of this pipe and create a fully structural liner that can take all of the loads of this pipe independent of the original host pipe. So that's this type of application. And once we've been, since we've been working with this system, we realized that this is an easy way to make a pipe. Now we have developed a technique that you can make a continuous pipe on site. So let's watch this video together and see how this can really change the whole industry of pipeline manufacturing.
This video shows a simple method to build a continuous infinite pipe on site. The process has been developed by quake wrap engineers according to Professor Ehsani's patented technique. Funding for this development through SBIR grants from the U.S. National Science Foundation and the U.S. Department of Agriculture is gratefully acknowledged. A heated, collapsible mandrel is provided. Layers of carbon or glass fabrics saturated with a special epoxy resin are wrapped around the mandrel. The strength and stiffness of the pipe is dependent on the type and number of layers of fabric being wrapped and will be designed by quake wrap engineers for each specific project. The mandrel is heated, and within a few minutes, the pipe is fully cured. Next, the mandrel is partially collapsed, and the finished pipe segment is pulled away, leaving a short segment of the pipe on the mandrel. Additional layers of fabric are similarly wrapped, cured, and the finished pipe is pulled away. This process continues for as long as needed to build a jointless pipe of desired length. The pipe can be used for new construction, for slip lining existing pipes, or for casing of wells. Advantages of infinite pipe include highest strength to weight ratio of any pipe, non-corroding materials with long service life, no cathodic protection is required, designed for any pressure, virtually no transportation cost, construction begins immediately upon placement of order, weighs less than 10% of conventional pipes. Infinite pipe is a green and sustainable technology. The 12-inch diameter pipe shown here has a wall thickness of only 0.18 inches, and it weighs about 4 pounds per foot. The pipe can resist an internal pressure of over 900 psi. The pipe surface is as smooth as fiberglass or PVC pipes. While the technique shown is ideal for projects with limited access, an automated wrapping machine is currently being designed for manufacturing larger diameter pipes. For more information, visit us online or call us.
So that was, something that can be done for pipe construction. But the last piece that I have are some, again, using that Sanebeach construction and repairing some other marine infrastructure, as you see here, for example, in the seawalls. So this was a project where we are repairing that red portion of the seawall that you see here is basically from the left side of this slide, and then it comes all the way to, coming to the right to end in front of that tank, basically about 900 or so feet of this waterfront structure. In this case, what the problem was that the sheet pile, which was a steel sheet pile, was corroded, and this particular plant, they had a lot of chemicals on the soil, and they were worried about leaching of these chemicals into the water, and EPA was going to find them, so they had to create, build an impervious wall in front of it and repair the wall. So in this case, we make these Sanebeach construction panels. We make them in 4 foot wide. For this project, they were 4 feet wide by about 20 feet long, and also some corner units, as you can see, plus some FRP glass FRP rebars, and these are all shipped into the job site. On the job site, we use J bolts that are anchored into the existing deteriorated sheet pile. So we use those J bolts, and then the 4 foot wide panels are put in front of the wall, and the overlapping joints about 4 inches along the edges of the 4 foot, they are overlapped and epoxy bonded together, so we create an impervious wall. And you see behind the wall, there are also the glass FRP rebars that are put inside of those cavities for additional strengthening. And we can use these whalers on the back of them, just as a temporary support during the placement of the grout. So as you notice, the wall, or basically the FRP wall has been created in front of that, in behind that overhang. And that's really one of the other points for you to keep in mind, is that because these materials, these panels are light, 2 divers can take them and install them without any equipment. As you see in this particular facility, the deck has an overhang, so you couldn't easily lift anything with a crane from the top and get it down there. But these are light enough that can be handled. They can also be taken behind those fenders that you see in front. So the lightweight is a major advantage on these projects, and of course the fact that it is durable and provides an impervious layer to protect the original wall from future corrosion. And these limited, as you noticed, the limited access that I mentioned. So here are the divers installing the crew, installing these 4-foot panels in front of the wall, and then once it's in place, it's the concrete or grout is applied. We can use the same technology for making not only flat panels but different shapes, and this application that we are doing for a project in Port of Galveston, in this case, the deck of the pier is very badly corroded from the underside. Now, in such applications, removal of the damaged concrete is very easy. You can sandblast it and remove that, but then to patch that and form that becomes a very expensive and costly process. So what we do is we can custom make these Sanebeach material to fit the exact shape of the underside of the pier. We can also include in here some additional reinforcing bars if needed, and then these get anchored, or from the underside they're lifted and bolted in place so they remain secure in place while the grout is poured, pumped from the top or from the bottom. And at the end, when this repair is completed, keep in mind that now we have a shell of impervious material around the structure, which not only helps us during the construction, but this will stay there as a permanent protection for the underside of this pier. So no more oxygen or corrosion will have access to this, and so the corrosion rate would significantly be reduced. And as you see here, this is a rendering of what these panels would look like. We can make them in different shapes based on the point of application, and they're all lifted and put in place like that. So with that, we've come to the end of my presentation. I hope you got some value out of this, and it kind of opened your eyes to different projects that you could hopefully use these materials on. A couple of things, unfortunately, this webinar, the way it is set up, we couldn't have a live interaction for question and answers, but my email address is listed here, so feel free to send me an email. I also, again, want to remind you that if you go to any of our websites, we have 3 of those: QuakeWrap, PileMedic, and PipeMedic. If you go to any of those, you will see a place where you can sign for a free consultation to discuss your project. If you think these systems can help you, we'd be happy to discuss it with you. And lastly, on our YouTube channel that you can visit and watch some of the videos that we have, and that might kind of give you an inspiration for how to apply these to some of your own projects. Again, I want to thank you for your attention, and my apologies that I couldn't be with you in person. I hope you have enjoyed the first day of this gathering of your annual conference, and hopefully you'll enjoy the rest of it as well. Have a wonderful day. Thank you.